Okay, so again, good morning, everybody. Welcome to our 27th class. So today, yesterday we talked about how to derive the Schrodinger equation, and I showed you that, well, the derivation was not very difficult. Now, so let me see what was the final expression for the Schrodinger equation. It was this. Okay. All right. So this is the Hamiltonian, and the IH apart the Schrodinger equation can be written as this statement. Okay. All right. So then after this, I talked about what happens when this state psi is an eigenstate of the Hamiltonian. So when it is an eigenstate of the Hamiltonian, the right-hand side of the Schrodinger equation, the action of the H operator basically just reduces to the energy, which is the eigenvalue, multiplied by the state. And so the resulting equation is an ordinary differential equation. There are no more operators. There's just d by dt, and we can integrate it, and we get that the equation for the state as a function of time is simply the state at some time originally, the initial time, multiplied by some phase. So that tells us that if the state of the system starts out, if the system starts out at an eigenstate, what happens is that it stays in that eigenstate. So any system which is in an energy eigenstate is in a stationary system. So this is not something completely abstract. It actually has meaningful consequences. As an example, if you consider an electron in, well, an atomic orbital, right? Now, these atomic orbitals are of the form, you have seen this in short, 1s2, 2s2, 2p1, and so on, right? So you fill up the orbitals one by one. And so let's say your electron happens, your configuration happens to be something like this, 2p1, and we'll leave it at that. So this is the electronic configuration for boron, I think. Boron, Fe5, or not nitrogen. Is it nitrogen? I think it's nitrogen, right? So anyways, so the point being that if you have an atom in like this in this electronic configuration, what happens? Atoms are stable, right? You don't have the electron in a hydrogen atom, for instance. If you just like a hydrogen atom, a hydrogen atom is a proton and an electron. Now this electron is in the 1s state, right? And you don't have the electron spontaneously jumping from 1s to 2s, right? That would not be very, very nice, right? And similarly, if you have, let's say lithium, what is lithium? Uh, lithium is the third element in the periodic table, right? So lithium has the orbital structure is 1s2, 2s1. Similarly, lithium also doesn't arbitrarily jump from 2s1. The electron doesn't jump from 2s1 to 2p and back or anything like that, right? The reason for that is that these are all energy eigenstates. There is a certain Hamiltonian for the electron in the in hydrogen and or in any atom, and these orbital states are energy eigenstates. They are solutions of the Hamiltonian. And since energy eigenstates are stationary, okay, this tells us that, well, this is one reason that atoms are stable. Otherwise, well, we would be in trouble. Okay. Now, let's look at some other examples of this. So we have to start talking about continuous systems, right? The Hamiltonian for, let's say, particle in a infinite potential well. So let's do that. Actually, we'll talk about that at Hamiltonian today. Okay.
In this case, are we
Sorry, I can't hear you.
eigenstates to be, so in this case, energy eigenstates are considered to be stationary, or are we proving it? Do we
Or are we what?
Proving it?
You have a proof, no? I showed you, no, that when this H psi, when this is an eigenstate, that means H psi becomes, this is an operator, this just becomes E psi, where E is the eigenvalue, right? Now, if you look at this equation, let me work it out again, okay? D by dt psi t is equal to E of psi t, okay? Now, this psi is it's a vector, right? So you might feel a little bit uncomfortable if I do something like this, if I do a manipulation like this, if I bring the psi t over here, let's say, and on the other hand, I write minus I by h bar E times dt, okay? This might make you feel a little bit uncomfortable because psi is a vector, so you might think, well, how do I divide by a vector? But one can show that, well, it's okay, it's completely okay to do this after the fact. Now one can integrate this equation, right? Now see, the thing is that if this was not an eigenstate, then this would be, E would be an operator. Instead of E, I would have the Hamiltonian. I would have minus I over h bar integral of the Hamiltonian times dt, right? Okay. Yes, then what would happen is, also on the left, when I do the integral, I would get log of psi of t, right, from some t naught to t. Okay, and on the right I would get whatever this integral is. It would be minus I by h bar integral from t naught to t h dt, where h is some operator, so it's a matrix. Okay, and then this log, I can take the exponential of both sides, so the log would become this expression would become log of psi t divided by psi t naught, right? Minus I h bar this integral t naught by t h dt. And so when I take the exponential of both sides, I would get that psi of t, right, is equal to psi of t naught. And again, this will be to the right. Exponent minus I by h bar integral t naught to t h dt okay. And now all of this is in the this integral of h is in the exponential, okay.
Yes, sir.
And as I said that, well, this is a, you can show after the fact, if you take the time derivative of both sides, you can show that this solution satisfies the original Schrodinger equation, okay. So if you're not satisfied with the method of derivation, then you can convince yourself that by taking the time derivative of, you get the original Schrodinger equation. So this is a solution of that equation. So now in this case, what you have is you have this integral of h, and then you have this exponential of that integral, that acting on psi, right?
Yes, sir.
Now now on if this h is if this state is an eigenstate to begin with, okay, then what will happen is h acting on the eigenstate will just give me a number e. So in that case, what will happen is this integral will reduce to an integral of a constant, which is just e. Just excuse me for 1 minute, I'll be right back. All right. Sorry about that. I was getting a call from my wife. So this integral is what? This is just e times t minus t naught, right? Okay. So the whole solution would become psi of t is equal to exponent minus I by h bar e times t minus t naught psi of t naught. Now what is this? This is the exponential is what? This is just a phase factor now, right? It's just a complex number.
Yes, sir.
It's just a complex number. This is just e to the sum I theta, right? Actually, I can write this as e to the minus I omega t. Where what is omega? Omega is equal to e by h bar, right? Now you can write this as e is equal to h bar omega, right? So this, what is this h bar? This is an angular frequency, right? Sorry, angular velocity. Because this angle, this exponent in the exponent, whatever is in the exponent is a phase, it's an angle, right? So if you have angle is something times t, then that something must be the angular velocity. Now angular velocity can be related to frequency, right? What is the relation? Omega is equal to 2 pi f. So then I can write E is equal to h bar, which is h by 2 pi multiplied by 2 pi f, which is equal to hf. Now, what is this? What is E is equal to HF? This is Planck's relation, right? This is Planck's equation. This equation tells us that the energy of a quantum is given by the some Planck's constant times the frequency of that quantum, right? So first of all, this justifies
Yes, sir.
the identification of this H with the energy, right? So when I derived Schrodinger's equation, right? I just told you, well, it's the energy. It's this eigenvalue is the energy, but you didn't really have a proper like reason for why it should be the case. But if you look at this solution for the case when you are in an eigenstate of H, and then you see that, well, it just becomes a complex phase. So then from purely dimensional arguments, you can see that this quantity is an energy. It has to be an energy, right? And moreover, this energy is given by H times F. So what is happening now? Let's say that psi of T naught, we start off in an eigenstate of the Hamiltonian, right? So let's say we start off in, so again, let's consider a spin 1/2 system, up and down, okay? So those are the eigenstates of energy, upstate and downstate. So let's say we start off in the upstate. Then what will happen? What is the state at a later time t? A state at a later time t is minus E times delta t by h bar multiplied by the upstate, right? So what happens? The state stays in the system stays in the upstate. It doesn't, there is no chance of the downstate. The probability for the downstate remains 0. The system stays in the upstate. Right? There is some complex phase, but that phase will cancel out when you measure the probability, right? I hope that that this is not too complicated to follow. If it is, please tell me. Then I can try to make things more simple. We'll look at more examples. As we look at more examples, things will become clearer. And by the way, so for homework 4, these are your homework problems. Okay, the first homework problem is this: prove that this Hamiltonian, this expression over here in the box, prove that it is Hermitian. Okay. Now the thing is that when you look at it, it doesn't look Hermitian, right? But it is Hermitian. You have to use a slight trick, and the trick is that you have to use Leibniz rule. What is Leibniz rule? For the derivative of two things, dAb is equal to a dv by dt plus b dA by dt. You have to use this, along with, you have to take the Hermitian conjugate of H, and then you have to use this. So I won't tell you more than that, because then otherwise I'll basically be. The second problem okay. Check that psi of t, this solution satisfies the Schrodinger equation. Okay, so you have to substitute this expression. You have to take the time derivative of this expression, and then you have to show that that time derivative satisfies this equation, not with the eigenvalue, without, because here in this solution the eigenvalue is not mentioned anywhere. All right, it's for an arbitrary. I think there is some lag in my. Can you all see my? It's not updating. I don't know why. Are you all with me? Yeah, okay, now it's showing up. Okay, good. All right. Okay, so yeah, because you have to show that this basically is a solution of Schrodinger's equation. So these are your first two problems. Okay. All right, now let's talk about something else. We'll talk about a particle in a box. All right. We have come all this way without talking about the typical problem of a particle in a box. So let's ask what is the Schrodinger equation for this problem, and let's try to solve it. Now, I talked about this problem, the setup of this problem. I talked about it a while back, a long time back. I don't know when that was. Okay, not that long ago. Yeah. So I talked about the setup of this problem, right? That you can imagine that you have an electron which is placed on a wire, one-dimensional wire, and then at 2 points, what you do is you apply a negative potential. So what that does is it creates a region where the electron becomes trapped, because if it goes to the left, it encounters a repulsive force. If it goes to the right, it encounters a repulsive force. So the potential energy within this region is less than the potential energy outside this region. Okay, so this was the setup. So let me write down first of all what is the value of the potential outside the box. We can set that to 0. Let's say this is region 1, region 2, and this is region 3. And the potential energy inside the box we can set to minus V0. Okay, now we can always choose. Remember that only the differences in potential energy matter, not the absolute values, right? So this is our potential energy function. We can write this potential energy function V of x as 0. So let me put some coordinates. I have not put any coordinates. Let me do that. So I'll say that this is the x-axis, and say this edge of the box is at plus L by 2. This edge is at minus L by 2. So the potential energy is 0 if x is greater than L by 2. Absolute value of x is greater than L by 2. And it's equal to minus V0 if absolute value of x is less than or equal to L by 2. This is a potential energy function, okay? Absolute value of x means that x is greater than L by 2 or x is less than minus L by 2. Okay, so this is regions 1 and 2, and this is region 3. Now, remember that the Hamiltonian is the total energy, right? So the total energy is what? It's the kinetic energy plus the potential energy. So we have the potential energy is what? Is the potential multiplied by the charge of the electron, right? So it's minus Vx times E. This is the potential energy. What is the kinetic energy? The kinetic energy of the electron is just P square by 2m, right? Or 1/2 mv square, you can write it like this also. But we work with, whenever we are talking about a Hamiltonian, in the Hamiltonian picture, our coordinates are always our phase space coordinates. Phase space means like the description of the state of the system is always given in terms of position and momentum. Okay, not in, so momentum is the fundamental variable, not the velocity. So our Hamiltonian can be written as P square by 2m minus E times, so the Hamiltonian, there are two different regions, right? 1, 2, and 3. In regions 1 and 2, sorry, in region 3, the Hamiltonian becomes, so this is the Hamiltonian when the particle is inside the box, and for the region outside the box, the Hamiltonian is just this. The potential is 0, right? In regions 1 and 2, okay? Okay. Now, so this is the classical Hamiltonian, okay? This is not the quantum operator. So now we want to write down for the Schrodinger equation, for the quantum system, we want a quantum operator, right? So this is the classical Hamiltonian. We want the quantum operator, right? So we want the operator version of the Hamiltonian. Now, for this, what do we need to do? We have the momentum, okay? And since we are working in one dimension, the momentum, there is only one number. So I won't put a vector sign, okay? It's understood P is equal to P of X. And I want to write the operator for the momentum, first of all. So P is just a number, right? It's the momentum of the particle. When I talk about the quantum particle, P has to become an operator. What should be this operator? Okay, that's the first thing. Similarly, there will be an operator for the position. So we have to understand what is the operator for the position. Okay. So now here, what we will do is I have talked about the transition from continuous to discrete to continuous systems, though you might have forgotten a bit. So let me just remind you that when you talk about continuous degrees of freedom, so what happens is that your function becomes your state vector becomes an infinite dimensional vector, right? So if I write down a discrete set of points, then each point is a position eigenstate. And if I take the limit that the number of points goes to infinity so that we get a real line, then what happens is my function becomes um, a continuous function of x. So this psi of x, so let me now go back and use this notation over here. So this is my state. Okay, first of all, this is the definition of my state. I don't know what the state is right now. This is just a definition. What is this x? What is x, this vector x? So remember, your particle is on the real line. The particle is well on a one-dimensional line. Okay. When you make a measurement of the position of the particle, what happens? You find that the particle is at a certain position x. Right? Let's say that this is the result of your measurement. Right? This is what you normally expect to be the case, right? You expect that if you measure the position, you get a number which is the position. But you could also get a different position x prime. This is also the result of measurement. Right? So what are the possible outcomes? Your possible outcomes are any position on the line. That is a possible outcome. So in terms of vectors, how should we write it? We should write it as this is one possible outcome, this is one possible outcome. And these are different outcomes, right? These are distinguishable, meaning that if your system is if your particle is at x, then it cannot be at x prime, right? When you make that measurement. And similarly, when it is at x prime, it cannot be at x. So since these are classically distinguishable, or at least that's what we assume, then this means that they have to be, their inner product will be 0. Okay, so what happens is you have an infinite dimensional Hilbert space which has a basis given by this set of vectors ket x, where x is a real number. Okay, and so this is infinite dimensional. Why? Because the dimensionality means is what? The dimensionality is the number of basis vectors of your state space, right? And since there is an infinite number of points on the real line, this is also infinite dimensional. Okay. So how do you write down the expression for any state? You write it down in this way, right? This is the basis vector. This is what psi of x is the coefficient of that basis vector, right? So this is exactly the same as writing if you have some vector v is equal to sum of I, let's say alpha I, and then you have some basis vector, let's say E. This is the same thing, only now we have a continuous vector. Okay, so now on this state we define the operator for position. The operator for position when it acts on this X state, what does the operator give us? It just gives us the eigenvalue is simply X. Okay. So if on my real line, right, I have my particle is at X is equal to, let's say, 10 centimeter. Then I act on this with this operator. What do I get? I get the answer is 10 centimeter. Right. This is my position. All right. Now, what about the momentum? Now, this is where all the quantum things actually come in. The momentum operator is written in this way, right? It's written as minus I times h bar times d by dx. Okay. Now, this is very strange. All of a sudden, this appears like magic, and you think, well, how is this making any sense? Like, so I will try to justify it now. Okay. So now imagine that you have some function, okay, some function of x, some function which is like this, let's say a times cosine k of x. Now what is this? This is a wave, right? This is a wave. And what is the wavelength? The wavelength is the interval over which the wave repeats itself, right? That means, so when does the wave repeat itself? When the argument changes by 2 pi. Right? This is fine. So this argument kx, this kx plus 2 pi, I can write this as k times x plus 2 pi by k, which I can now write as k times x plus lambda. So whenever the position x changes by an amount lambda, the wave remains the same. So that tells me that 2 pi by k, which is equal to lambda, this is the wavelength of my function, right? Fine. Now let me ask what happens when I take this momentum operator and I act on this function with this momentum operator. Okay. So I take my momentum operator and I act on this function with this momentum operator. What do I get? Well, the momentum operator is simply a derivative, right? D by dx. Okay. So if I act on it with the momentum operator, what do I get? I get d by dx of cosine, which is minus sine, and I get a factor of k. So I get I h bar k a times sine kx. Okay. But now here I have this function f of x, and on the right side I don't have the same function anymore, right? But I know that, well, if I take a second derivative, so if I say p square, if I take this function f and I act on it with the operator p one more time, that means I have acted on this function with p once, and then I act on it again. So that means that becomes P square. What will I get? Well, this will be P acting on IHK times A times sine of Kx. Okay. Now again, this is just the derivative. So I will get minus K, sorry, I'll get K cosine Kx. So I'll get IH bar K square times A times cosine Kx. Okay. Everybody with me? I hope. Okay.
Yes, sir.
So what is this? This tells me that if I take P square and act on A cosine Kx, oh right, and when I put the second P, I'll get a minus H bar square because there's a factor of H bar that I forgot. IH bar. So I'll get minus H bar square K square. Okay. Now what does this tell me? This tells me that this A cosine Kx is an eigenstate, right? This is an eigenvalue equation. Now you can see this, right? This is my eigenstate, this is my operator. When I act on the eigenstate with the operator, I get the eigenstate multiplied by some eigenvalue. So this is an eigenstate of my operator. Which operator? P square operator. With eigenvalue, what is the eigenvalue? Minus H bar square K square. Okay. Now what is this minus H bar square K square? Okay. Let's go back and again remind ourselves that K is equal to 2 pi divided by the wavelength of the particle, or the particle of the whatever the function. K is equal to 2 pi by lambda. So that means H bar K, what is H bar K? H bar K is H by 2 pi. K is 2 pi by lambda. What is this? This is H by lambda. Okay. What is H by lambda? Anybody?
Energy.
H by lambda, man. H by lambda.
Momentum.
E by C.
Huh?
E by C.
E by C. And what is E by C? Whose hypothesis is this? This is a hypothesis.
So Shashwat,
Let me.
from HC by lambda we'll get C by C.
No, but that's fine. But then what is E by C? What are the units of E by C?
Momentum.
Momentum. And this is which hypothesis?
Not remember.
D hypothesis. D what hypothesis?
Broil or somebody.
De Broglie.
De Broglie's hypothesis.
Okay.
याद आया? Right?
Yes, sir.
What was de Broglie's hypothesis? That a particle with a certain momentum p, right, has a wavelength lambda is equal to h by p. Remember that? So now we have reversed de Broglie's hypothesis, and you can see now what is the result, that the eigenvalue of this p square operator is equal to minus h bar square k square. Okay. And what is h bar k? H bar k is h by lambda. What is h by lambda? It is p, the classical momentum. So what is h bar square k square? It's equal to minus p square. Where now this p is the classical momentum. So the eigenvalue of, so I will now write eigenvalue of minus of the p square operator is classical momentum squared, p squared. Right? So this means I can identify, if you take the square root, you can identify I times p hat as the operator for momentum. Right? So do you see this? Right? So if I have something whose eigenvalue gives me the quantity squared, then the square root of that is the corresponding operator for that quantity.
Sir,
Yeah.
sir, the eigenvalue of p square, is it minus h bar square k square? Does that minus sign be there? Because when you multiply minus I h bar with I h bar, you'll get positive, right?
Minus I h bar. So I'll take minus I h bar, then I take the derivative. So I get
There'll be extra I
plus I h
square,
bar.
right?
Then I have another minus I h bar. I'll get plus h bar. I knew that there was some ghapla somewhere. Thank you for clearing that up. So this is with eigenvalue plus h bar square. That makes more sense. Eigenvalue of p square is, eigenvalue of p hat square is p square. So we don't need to take this ip nonsense. Okay. Okay. So this p square has the eigenvalue p square. P square operators, p operator square has eigenvalue momentum, classical momentum squared. Okay. So basically, see, all of this rests on the assumption that what is this function? This function corresponds to a particle with a wave, with a certain wavelength, right? And that assumption comes from de Broglie's something hypothesis. So that's why this guy, so I have justified it after the fact. Okay. And so it takes a little bit of getting used to. It's not obvious why this should be the case. All right, so I'll leave it there, and I'll ask you guys if you have any questions. Questions?
Sir, in that energy, like phi of t, you told energy stationary states. Isn't that true only if Hamiltonian is a constant, like it is not time independent or position independent? Like
yeah, you're right. So I'm assuming that a Hamiltonian is time independent.
And sir, it should be position independent also, right? Like if my position, if my what is that? Potential changes with position, then even
No,
eigenvalues changes with time.
No, that's not correct. So if you look at a very simple example, you can consider the Hamiltonian for a free particle. The Hamiltonian for a free particle. This is not.
So, but here it's a
This
constant.
depends on
right?
the. One second.
Sorry.
This is not a constant, right? It's a function of the position, right? It's a step function, but it's a function of the position. So instead of a constant potential, I can always take something which is not constant. Like I can take a harmonic oscillator potential. Okay, I can, instead of V naught, I can take something like 1/2 kx squared, which is the harmonic oscillator potential energy.
Okay.
In that case also, I will get eigenstates. Those eigenstates will have constant energies.
So,
They will
but
be stationary states.
how, sir? Like with position, so if a particle is moving,
So
then it will...
we'll talk about this in later classes. I mean, if you don't see how, you will see how. Okay. So obviously I can't tell you now because it will take too long. Okay. But yeah, I mean, you do have eigenstates. So H does not have to be position independent. H can be, because another thing is that I gave you this example of the hydrogen atom.
Yes, sir.
In this case, the Hamiltonian is not position independent.
So, but it's path independent, right? Like,
Hey, Baba, there's a difference between path independence and position independence. Path independence is a completely different thing. Path independence is the statement that if you go from point A to point B, the work done in going from point A to point B depends only on the endpoints.
Endpoints, okay.
That means your potential is conservative. Okay.
Okay.
But it doesn't mean your potential is a constant.
Okay. So,
Right? If you have a Coulomb potential, your potential is conservative. But is your potential a constant?
No.
No, it's not constant, right? So don't confuse those two things. Conservative and these are two separate things. Here, in this case, your potential need not be conservative also. Okay. Even if you have a non-conservative potential, you can get eigenstates for that potential, that Hamiltonian also.
Okay.
So I've given you guys two homework problems. One is to show that definition of the Hamiltonian is Hermitian, and the second one is to show that this expression satisfies Schrodinger's equation. Okay. Then I'll give you a few more problems tomorrow.